Hello viewers, my today's lecture is on integrative approach in construction of underground structures. This approach fosters a collective action across design and construction. There is a lot of interdependence between design and construction of underground structures. Therefore, a review of the design is need to be performed iteratively with renewed parameters as these are observed during various stages of construction, and these thus become complementary necessities of the underground structures. The complementary necessities in the design and construction of the big underground structures need to be understood from the very concepts. So I would like to cover these concepts along with taking through a case study and also demonstrating the consequences that happened during the course of designs and constructions. The mechanism and structural behavior involved as presented in the lecture are supported by international literature and are demonstrated to be corroborated in the Norwegian Geotechnical Institute's findings and 3D numerical analysis by National Institute of Rock Mechanics. I'll start with describing the three elements of underground structures, which are rock, rock mass, and underground structure itself. The geology of underground site would invariably be involving, besides a parent rock, a number of different types of other rocks varying from soft to hard, etc., present at the location of underground structures. These conglomerate assemblage of these various rocks of different qualities are further influenced by the quality, spacing, orientation, and type of the filling material in the various joints present, which comprise the rock mass. Now, the underground structure is influenced by the rock mass behavior it is situated in. Rock mass stability would rather proper nomenclature for this would be rock mass ability and structural stability. Rock mass ability to maintain its structure in the vicinity of the excavation boundary is influenced by several parameters, but the following three factors are the most important. That is degree of jointing, that is the block size, the joint frictions, and the stress present in the rock mass. Whereas the structure stability is influenced when rock mass in the much greater depths around get influenced due to presence of adversely oriented, strongly developed, inclined structural features. It is important to note that the relationship between the rock mass characteristics and the geometry and orientation of the proposed excavation in presence of the strongly developed inclined structural features decides the stability of the underground structure. Let us acquaint ourselves with the stresses around an excavation. There are radial, tangential, and shear stresses present at any excavated section, which are defined by the following shown equations. These radial, tangential, and shear stresses can further be composed into two stresses at each point at the section called maximum principal stress and minimum principal stress. Both radial stress and the shear stress are zero at the boundary of the excavated opening. This figure shows the variation in the boundary stress at an excavated section. The boundary stress varies along the periphery, and it is depicted that the ratio of boundary stress to the vertical applied stress is shown on the vertical axis in the graph, and the ratio of horizontal applied stress to the vertical applied stress is mentioned in the horizontal axis. So as the ratio of horizontal applied stress to the vertical applied stress approaches 1, the boundary stress at this point and this point, which are at theta 90 degree and 270 degree, they vary from 3 to something like 2.5. And for the points like at the invert and at the crown, the stresses varies from the tension reach till the ratio of horizontal applied stress to the vertical stress is of the order of around 3, and then it increases to reach to around 2.5 when the ratio of horizontal applied stress to the vertical applied stress approaches 1. The variation of tangential stress is depicted in this diagram. Theoretically, the ratio of side wall stress sigma theta to the vertical applied stress is of the order of 3 at the periphery of the opening with a radius A, when the ratio of radial distance r to the whole radius A increases, the tangential stress starts decreasing and it becomes almost a unity when the radial distance r is of the order of 3 times the radius of the hole or the tunnel. I would like to refer to an article, Design Principles for Underground Rock Sport by Professor Charlie of Norwegian University of Science and Technology, which gives the distribution of major principal stresses in rock mass after excavation. The previously seen stresses, tangential stresses, now in practical they would have a distribution as shown in this graph. As the distance to the tunnel wall increases, the tangential stress first increases and thereafter the tangential stress starts decreasing, and in this example the maximum tangential stress is at a distance of around 2.5 meters from the excavated wall at that section. There is a zone called failure zone present around the excavated section to some distance, and thereafter this tangential stress is maximum in a certain zone after this failed zone. There is a natural pressure arch formed in the rock mass in a certain distance behind the tunnel wall. This failure zone has lesser tangential stresses, and after a certain distance, when this failure zone is finished and more competent rock is present around, in that competent rock the tangential stresses increase and thereafter they decrease and becomes almost constant. In this zone where the tangential stresses increase to its maximum, a natural pressure arch is created which supports all the rock loads from above and sides that are coming on this failure zone. Now the science of tunneling is about stabilizing that failure zone and reinforcing that failure zone and pre-stressing the failure zone to arrest its further yielding. Stitching the failure zone to the natural pressure arch around it and beyond to the sound rock if the failure zone is excessive is an additional. This fourth measure is required when there is a excessive failure zone around. Most of the cases, stabilizing the failure zone by various methods, also if required reinforcing the failure zone, and also if required pre-stressing the failure zone stabilizes the excavated profile. Let us look into what defines the rock mass stability. The joint spacing, when is considerably small along some zones in the surrounding rock, then such zones are called fracture zones. In hard rocks, deformations will occur as shear displacements along joints. The friction along the joints will therefore be significant for the rock mass stability. Joint friction is dependent on joint roughness, thickness, and type and condition of mineral fillings. Very rough joints, joints with no fillings, or joints with only a thin, hard mineral filling will be favorable for rock mass stability. The parameters with number of joints, roughness of joints, and degree of alterations play a very important role, even more than the orientation of joints, as number of joint sets determine the degree of freedom of various blocks movement. Presence of moderate stresses are usually favorable for stability of excavated section. Low stresses are often unfavorable for the stability. In rock masses intersected by zones of weak mineral fillings such as clay or crushed rock, the stress situation may vary considerably within relatively small areas. Experience from tunnel projects in Norway has shown that if the magnitude of the major principal stress approaches about one-fifth of the compressive strength of the rock, then spalling may occur. And if tangential stresses exceed the magnitude of rock compressive strength, then squeezing may occur. The anisotropy of the rock mass plays an important role when designing the rock sport. On the other hand, smooth surface and or a thick filling of a soft mineral will result in low friction and poor stability. In soft rocks, where deformation is less dependent on of joints, the joint friction factor is less significant. Now, after talking of the rock mass stability, let us see what comprises stability of underground structures. The geotechnic structural features, more significantly if these are inclined structural features like shear zones and faults, besides multiplicity of adjacent caverns and the rock cover available to the excavated caverns or tunnels, create asymmetrical stress conditions around the excavated caverns which govern the stability conditions of the underground structures. Further, about the structural stability of underground opening, the vertical stress in a rock mass commonly depends on the depth below the surface. However, the tectonic stresses and anisotropic stresses due to topography can be more influential in some areas. Stability of the underground excavation will generally depend on the stress magnitude in relation to the rock strength. The failure of the hard rock depends upon the magnitudes of the major and minor principal stresses acting at the point of consideration. The dip and drive direction also affect the choice of orientation of the tunnel. For example, the tunnel oriented such that the dominant joint set strikes perpendicular to the tunnel axis with a dip of 30 degrees against the drive direction is an unfavorable condition. We'll talk about this in later slides more effectively. The renowned authors Hook and Brown, in their design of underground excavations in rock article, they mention the influence of structural geology on stability of underground structures. It says, in hard rock masses with strongly developed inclined structural features, excavation stability may be dominated by gravity falls and sliding along inclined discontinuities. Rock classification systems thus become inadequate. So in case of hard rock masses which have strongly developed inclined structural features, its excavation stability will not be governed by, if designed by rock classification systems alone. Instability due to adverse structural geology affects such structures detailed geological mapping of the borehole core, surface exposures, and exploratory adits and shafts need to be done, and it needs to be evaluated that can stability be improved by relocation and or reorientation of the excavated sections or caverns. The answer could be yes or no. That is, either the stability of the excavated cavern can be improved by relocation, reorientation, or no, it cannot be improved. Depending upon, if it is yes, then proper designs of excavation with presence of close geological observation and local support as required needs to be done. But if answer is no, that the stability cannot be improved by relocation, then design of support to prevent gravity falls and to reinforce potential fracture zones needs to be resorted to. At this stage, we need to evaluate that can adequate support be provided to ensure long-term stability. That means if relocation could not be seen to be improving the stability conditions, then also if there are no adequate supports can be designed to be provided to ensure long-term stability, then if no, then Hook and Brown suggests that this site needs to be rejected. So this is a very important information which I'll later connect to the case study, that in hard rocks masses with strongly developed inclined structural features, relocation needs to be a first resort to improve the stability. But if relocation and reorientation is not possible or is not done, then adequate analysis and designs need to be provided to support the excavated profiles, and if adequate designs provisions cannot be made for certain reasons, then it is wise to reject such site. Let us understand the concepts of rock mass behavior and structural stability from a case study of Punatsangchhu-II hydroelectric project. Punatsangchhu-II is located towards the middle west of Bhutan. The layout of the project is that all the underground features are on the right side of the Punatsangchhu river, because the right side hill is relatively having better geological features than the left hill. There was a powerhouse earlier proposed as a surface powerhouse, but for some reasons it was decided that the powerhouse should be located underground, which necessitated introduction of surge shaft and a tail-race tunnel, which was almost 3 kilometers long. Not going into the reasons why it was thought of shifting, let us go further that now the powerhouse is underground. This slide shows the features of the underground powerhouse. There is 8.6 kilometer 11 meter diameter headrest tunnel. There is a restricted orifice open to sky 31 meter dia, 137 meter high surge shaft. There are pressure shafts vertical circular steel lined of 5.5 meter diameter, 995 meter long. Machine hall is 236 meter long, 23 meter wide and 51 meter high. The height of the powerhouse machine hall is 51 meter. The installed capacity is 6 units of 170 megawatt each. Gross head is 266 meter. The transformer hall is 215 meter long, 14 meter wide and 26.5 meter height. There is a Downstream Surge Gallery, which is 314 meter long, 19 meter wide and 58.5 meter height. Because that the powerhouse has been shifted to the underground, the Downstream Surge Gallery becomes necessary as the tail race tunnel of 3.1 kilometer gets involved. So now there are three adjacent caverns: powerhouse machine hall 51 meter height, transformer hall 26.5 meter height and downstream surge gallery of 58.5 meter height. This is a 3D view of the powerhouse complex. This is downstream surge gallery, which is 314 meter long and 58 meter height. This is transformer hall and this is powerhouse machine hall, which is again 58.5 meter height. They have 40 meter each of rock pillar provided between the two adjacent caverns at each location. Now, 2nd March 2016 is an important date in the course of construction of these three caverns. On 2nd March 2016, the stage of excavation reached in the three caverns was that the machine hall had been excavated throughout its full height. All the tunnels connecting transformer hall to the machine hall had been excavated. The transformer hall had been excavated for its full height. The downstream surge gallery had been excavated to almost its 2/3 height. Out of 58 meter height, it was excavated in different reaches ranging from 30 meter to 45 meter of its depth. There was a huge rock mass failure happened in the downstream surge gallery on 3rd March 2016. 6 technicians got buried dead under the falling muck. 3 of the bodies could be recovered and 3 of the bodies still lay buried unrecovered. This 30 to 45 meter of height excavated on the downstream surge gallery got filled up with fallen muck almost in its middle length over a distance of around some 100 meters out of the 314 meter of its full length. at the base of the fallen mark. It is important to note that the massive rock mass failure had happened 3 years after the excavation of the crown. The rockfall took place in a very short time, leading to formation of a huge cavity above ground. For almost full 3 years, the cavern, when it was being excavated through its height of around 58 meters, and it had reached to a depth of 30 meter to 45 meter excavation, then in a very short time, the rockfall in its crown had happened, which made a very huge cavity above the crown. The fallen rock mass comprises of variable size of large to fragmented rock pieces, sandy clay and dry clay fractions. The fallen big rock blocks are ranging of the size of 9 meter into 1.5 meter into 3 meter size. It was later on studied and found that the cavity formed above the crown in the Downstream Surge Gallery is of the magnitude of 91 meter height, 75 meter long and 45 meter wide. This cavity is 91 meter high, 75 meter long in this direction and 45 meter wide in this direction at its maximum extremities point. This needs to study vulnerability of caverns to structural instability. Punatsangchhu-II projects caverns, powerhouse machine hall, transformer hall, and the Downstream Surge Gallery. They are oriented in north 5 degree west. The foliation joints have a low dip of around 10 to 15 degree, directions southwest to northwest. The spacing of such joints is 0.2 to 0.3 meter. Besides that, a major shear zone of inclination of dip of 45 degree to 60 degree, this which I have marked with the red lines, cuts through the height of the caverns with an orientation of north 30 degree east. So it's intriguing to find out what was peculiarly different in Downstream Surge Gallery cavern than powerhouse and transformer hall caverns, that the failure happened in the Downstream Surge Gallery. Why did the rockfall happen in the Downstream Surge Gallery after 3 years of the crown standing intact is a point of interest. Why did the rock mass failure happen in Downstream Surge Gallery while the powerhouse cavern with more depth of around 58.5 meter already stood excavated as compared to the depth of excavated of 30 to 45 meter in Downstream Surge Gallery? Why did the rock mass failure happen in Downstream Surge Gallery while the powerhouse cavern had its both walls having multiple openings? There are 6 pressure shafts entering into the left side wall of the powerhouse cavern, and there are 6 draft tube tunnels coming out of the right wall, and there are multiple tunnels connecting powerhouse machine hall to the transformer hall which will carry the bus ducts. There will be emergency exit, connecting tunnel. So there are multiple openings in the walls of both the long walls of the powerhouse machine hall. If this feature is considered, then why should the failure not happen in powerhouse and it happened in Downstream Surge Gallery, which doesn't have any opening till the level of excavated height? Why did the rock mass in the crown failed while the excavation was underway in benching 45 meters below the crown? Why did the rock mass fail suddenly and extended to make a 91-meter high cavity with very large base? And why did the cavity created of 91 meter into 75-meter length and 45-meter width size remain without progressing further in size to a similar scale for these years after March 2016 till date without being stabilized or supported by any strengthening having been done? Very lately now, this cavity of 91 meter into 75 meter into 45 meter has been started with filling back with flowable concrete. But from 2016 March till very recently, this cavity stood untreated, unsupported, unstabilized for all these years, and it had not progressed further in a size. These are some of the very intriguing questions that come to one's observation. Now, the first and the foremost observation or requirement to be mentioned is that design of an underground structure cannot remain exclusive. By this I mean that it cannot be that design done once would hold good for all the times of the construction of the caverns. It needs to have iterative integration of design, geology, and execution limitations to be taken together. It becomes a necessity to keep iteratively integrating design, geology, and executional limitations throughout at various stages of construction of underground structure. NATM and NMT adopt approach of integration of design and site conditions as excavation proceeds. This is well known, and these NATM and NMT approaches are vastly used as design and construction methods of tunneling. New Austrian tunneling method, NATM, was developed in 1957 and 1965 in Austria. It is referred to as design-as-you-go approach to tunneling, providing an optimized support based on observed ground conditions. It is a design-as-you-monitor approach based on observed convergence and divergence in the lining as well as prevailing rock conditions. Also known as sequential tunneling method, it takes advantage of the inherent geological strength available in the surrounding rock mass to stabilize the tunnel. It integrates the principles of the behavior of rock masses under load and monitoring the performance of the underground construction during the construction. The design philosophy of NATM, according to Brown, The key features of the design philosophy refer to the strength of the ground around a tunnel is deliberately mobilized to the maximum extent possible. Mobilization of ground strength is achieved by allowing controlled deformation of the ground. Initial primary support is installed having load deformation characteristics appropriate to the ground conditions, and the installation is timed with respect to ground deformations. Instrumentation is installed to monitor deformations in the initial support system as well as to form the basis of varying the initial support design and the sequence of excavation. NATM is more of a construction method. When NATM is seen as a construction method, the key features are the tunnel is sequentially excavated and supported, and the excavation sequences can be varied. The initial ground support is provided by shotcrete in combination with fiber or welded wire fabric reinforcement, steel arches, usually lattice girders, and sometimes ground reinforcement, that is soil nails or spiling, are resorted to. The permanent support is usually, but not always, a cast in place concrete lining. Support provided as required by encountered ground conditions. So this becomes the basis of the approach that supports are provided as required by the encountered ground conditions. So the design of the support system is not exclusive. It takes into consideration the various ground conditions, and accordingly the permanent supports are designed and provided. The 7 features of NATM can be listed as mobilization of strength of the rock mass, shotcrete protection, measurements of deformations, flexible support. The primary lining is a thin and reflects recent strata conditions. Active rather than passive support is used, and the tunnel is strengthened not by a thicker concrete lining but by flexible combination of rock bolts and wire mesh. Closing of invert. Quickly closing the invert and creating a load bearing ring is important. Contractual arrangements need to be made for taking into consideration all these flexibilities of changing the designs of the supports as required by the ground conditions. Most important is rock mass classification determines support measures. There are several main rock classes for tunnels and corresponding support system for each in NATM. These serve as guidelines for tunnel reinforcement. So NATM is an approach of rock mass classification to determine the support measures. However, it is found that NATM is not suitable for overbreaks in excavation. NATM appears most suitable for soft ground, which can be machined or hand excavated, where jointing and overbreak are not dominant, where a smooth profile can often be formed, and where a complete load-bearing ring can and often should be established. Monitoring appears to play a significant part in deciding on the timing and extent of secondary support. So monitoring becomes very important, and this decides timing and extent of secondary support. Using the surrounding ground as a main load-bearing component is not an exclusive NATM philosophy, though it is essential practice and is often inevitable. Then let us see how is Norwegian method of tunneling different. While NATM is suitable for soft ground and which can be machined or hand excavated, where jointing and overbreaks are not dominant. So what to be done for where the jointing and overbreaks are dominant, the Norwegian method of tunneling was adopted. NMT appears most suitable for harder ground where jointing and overbreak are dominant, and where drill and blasting or hard rocks TBMs are most usual methods of excavation. Bolting is the dominant form of rock sport since it mobilizes the strength of the surrounding rock mass in the best possible way. So in Norwegian method of tunneling, bolting is the dominant form of rock sport. Now steel sets are found inappropriate in overbreaks. Rigid steel sets or lattice girders are inappropriate in harder rocks due to the potential overbreak. Potentially unstable rock masses with clay-filled joints and discontinuities will increasingly need shotcrete and fiber-reinforced shotcrete to supplement the systematic bolting. In the Norwegian method, the potentially unstable rock masses with clay-filled joints and discontinuities will increasingly need shotcrete and fiber-reinforced shotcrete to supplement the systematic bolting. It can be stated with some certainty that bolting and fiber-reinforced shotcrete are the two most versatile tunnel sport methods yet devised, because they can be applied to any profile as temporary or as permanent support just by changing thickness and bolt spacing. A thick load-bearing ring reinforced rib of shotcrete can be formed as needed and matches an uneven profile better than lattice girders or steel sets. Now, Norwegian method is based on quantitative representation of rock masses rather than a classification which was resorted to in NATM. NMT is a method that describes the rock mass in quantitative Q system rather than just qualitative terms. The important point is NMT's forward prediction of conditions and modifications for unexpected conditions should each be done as early as accurately as possible. Now, as a difference from NATM, where the observations of deformations was the criteria of deciding the permanent rock sport, in Norwegian method, modifications for unexpected conditions are done early and accurately based on the forward prediction of conditions. Not based on the observations, but forward prediction of conditions. Briefly, I'll go through quantitative representation of rock mass, the definition of Q. The Q system is forward predictive method and therefore differs significantly from NATM methods, which apparently depend on monitoring to decide on the timing and amount of additional supports to finally place the rock in correct class. Now, essential features of Norwegian method are areas of its usual applications are jointed rock, harder end of scale 3 to 300 MPa, clay bearing zones, stress slabbing, the Q ranging from 0.001 to 10. Methods of excavation could be drill and blast, hard rock TBM, hand excavation in clay zones. Temporary support and permanent supports may be of the following: mostly of bolting and reinforced shotcrete. Dry process shotcrete, not used. Steel sets or lattice girders, not used. Bolting and fiber reinforced shotcrete is usually the final support. Rock mass characterization is by predicting rock mass quality and support needs, updating of both during tunneling, monitoring in critical cases only. The NMT gives low cost and rapid advances rate. Preliminary design is based on field mapping, drill core logging, and seismic interpretation using newly developed VP-Q relationships. Rock mass quality is described by the Q value. Final spot is selected during tunnel construction based on tunnel logging and the use of Q system spot recommendations. These are the rock mass classifications, and based on the Q values, the spacing and thickness of shotcrete is described in these graphs. Numerical verification of one or more of the various permanent support classes is performed in special cases. Using the distinct element jointed two-dimensional UDEC VB or three-dimensional 3-deck computer codes is a rarely resorted to through numerical verification. Mostly the design supports in Norwegian method would come from this graph, which has parameters of Q and the span of the opening. In Norwegian method of tunneling, excavation usually by drill and blast is tailored to the rock conditions. NMT is also applied in tunnels excavated by road header or hydraulic breaker outside Norway. The temporary support such as bolt or bolt plus fiber reinforced shotcrete is approved as a part of the permanent support. In poor conditions, pre-grouting, spiling and use of rib reinforced shotcrete arches up to the face may be used. Cast concrete may also be needed as temporary support in some cases, cast against an articulated shield. The permanent support class is chosen during tunnel advance and will depend on the rock conditions, which are symmetrically logged. Deformation measurements will usually be used in very and extremely poor rock as confirmation of the support class. However, it may be dangerous to assume that reducing rates of deformation signals stable conditions. Now, there are limitations of NMT also. The Q-based design NMT is not applicable for powerhouse complex caverns with height greater than 50 meter in rock mass of very poor and poor classification. According to Norwegian Geotechnical Institute, even the quantitative Q-based design NMT is not applicable where excessive overbreaks happen. The finite element based numerical analysis are suitable in such conditions where the Q-based design NMTs remain inapplicable due to excessive overbreaks, or where the rock mass is very poor and of poor classification when the height of the caverns are more than 50 meter. In those circumstances, the finite element based numerical analysis are suitable only. So, the basic principles of a justified design of underground excavation would then be about making quantitative predictions on the number, inclination, and orientation of geological features and of the possible mechanical properties of rock mass containing these features are thus the inputs to the design of any structure to be constructed which involves excavation of larger magnitude. So now we are talking of basic principles of justified design for large underground excavations. Making quantitative predictions on the number, inclination, and orientation of geological features and of the possible mechanical properties of the rock mass containing these features are the inputs to the design of any structure to be constructed which involves excavation of larger magnitude. Use of some form of the rock quality index to determine the support requirements is usually the adopted approach. Any change noticed in quantitative representation of these parameters at any stage naturally calls for review of the design and also its methodology, depending upon the limitations of the methodology, taking account of impact of these parameters. So to start with, a rock quality index is the parameter which determines the support requirements, and at various stages of the excavation, when there is any change noticed in the quantitative representation of these parameters based on which the initial design was done, it calls for a review of the design and its methodology depending upon the limitations of the methodology. Further, if it is somehow established on the basis of the geological interpretation that stability problems are likely to be encountered, it becomes necessary to embark upon a more methodical and scientific approach to ascertain the structural stability of the entire rock mass in the vicinity of the excavated opening, that is cavern and tunnels. This is very important that at any stage during the excavation of large caverns, if it is somehow established, many geological features will be exposed during the excavation of the large caverns, and based on those geological conditions or site conditions, if it is justifiably seen that stability problems are likely to be encountered, then it becomes necessary to embark upon a more methodical rather than just based on rock quality index, more methodical and scientific approaches to ascertain the structural stability of the entire rock mass in the vicinity of excavated opening becomes a necessity. Thus, the science of tunneling is design as excavation advances, assessing rock mass behavior and support needs which shall suffice when excavation proceeds further, either through empirical approach, and if empirical approach becomes redundant, then resorting to numerical modeling. Both of these approaches require predicting rock mass quality, predicting support requirements, then updating both predictions during progress of tunneling. That means the rock mass quality prediction is also to be reviewed, and based on that, the support requirements predicted needs also be reviewed during the progress of tunneling. Monitoring rock mass behavior through instrumentation. Because the height of the excavations caverns would be large, therefore the monitoring of rock mass behavior through instrumentation becomes also a necessity. Based on how the rock mass is behaving, one would need to switch to updating the numerical modeling, review of designs and adopting corrective measures in the critical cases. In critical cases, it would require change of design methodology and adopting corrective measures. The complementary design requirements of deep caverns thus are: we see that in tunneling, NATM and NTM are workable because the review of design and modification in rock sport measures are possible even when excavation had progressed considerably. Because of the linear uh, alignment or linear feature of the tunnels, it is possible to make changes in the reaches which have been excavated already based on the requirements or the behavior of the supports seen when the tunnel progresses. But the vertical progress of excavation in the caverns, in very deep and large caverns, the excavation is progressing vertically downward. So the vertical progress of excavation in caverns demand a deterministic analysis to ensure structure's stability beforehand at each stage of excavation before proceeding further down in benching. Therefore, a more strict vigil on site conditions, foresight in geological predictions, and accurate evaluation of structural stability are prerequisites to apply a complementary approach of design and construction of deep caverns. So, in case of construction of deep caverns, there needs to be a constant strict vigil on the site conditions, foresight in geological predictions, and accurate evaluation of structural stability are the prerequisites. This calls for integrating the field conditions, analysis, and design, and that too to be resorted to iteratively all through the construction stages. This approach of integrating the field conditions, analysis, and design becomes indispensable in case of caverns of very large depths. Iterative integration of design and construction in underground structure. Design of underground structures need to evolve along with the advance in its excavation. Approach of iterative integration of design and construction involves adequate geological investigation of the site and investigation of in situ stresses, designing orientation and layout of the underground structure, preliminary analysis of stability of underground structures to be done beforehand, construction stage investigation and review of geology and structural features during pilot or central gullet excavations need to be done. Review of design of orientation and layout of the underground structures as the need necessitates. Review of stability analysis based on revised geological features which get revealed during pilot or central gullet excavation. Instrumentation during excavation. Validation and review of designs based on instrumentation at various stages of excavation. Review of stability analysis of the underground structure at each critical stage of excavation and further revelations of geology. So all these 9 steps comprise the iterative integration of design and construction in underground structure. In the coming slides, we'll come to see the importance of all these steps of design and construction to be done iteratively, and if not done so, what are the consequences would be demonstrated in the coming slides, quoting the various international literatures in support of what we'll discuss further. Discussion and demonstration of importance and appropriateness of each of these integrative steps for inclusive design and construction. First point is importance of adequate and appropriate site investigations. Besides geological survey of the exposed geological features, it is important to investigate the site of underground structures with adequate numbers of borehole investigations and also preferably by cross-hole tomography. For long tunnels, the borehole locations, besides being guided by exposed geological features at surface, should be done at regular intervals on its alignment and near each location of tunnel junctions. Deep and long caverns should be investigated through at least 4 to 5 number of boreholes, 2 vertical boreholes located one near each end and preferably one additional hole at center, and remaining 2 holes should be inclined boreholes so that the entire length and breadth of the cavern and the rock mass above its crown is also studied. The advice of geologists based on geological investigation should be respected. Engineering designs may not always be sufficient to confront geological might, especially if are not judicious. At least 4 boreholes were required to cover 314-meter long and 58-meter deep cavern of Punatsangchhu-II Downstream Surge Gallery. The Downstream Surge Gallery of Punatsangchhu-II was having a length of 314 meter and depth of 58 meter. There was only one borehole available, DSC-1, at one end of the Downstream Surge Gallery. The rest of the remaining 314 meter length and 58 meter of depth of the Downstream Surge Gallery cavern remained unrepresented by any geological study. Therefore, it missed to detect a mega shear zone and class 4 and class 5 rock masses which were actually present. This was a mega shear zone which was missed to be represented by when seen through this borehole, and there were class 4 and class 5 classification of rock masses actually present here, which were crushed and sheared lithogranite and intrusive pegmatite. These remained unrepresented. Flat and thinly foliated class 5 and class 4, fractured and blocky rock mass of class 3 and class 4, which comprise this zone lying after the shear zone, remained unrepresented in the study done through this sole borehole DSC-1. The Geological Survey of India had advised to do borehole here also, but it was missed, and therefore the only one hole was available. Studies based on this borehole missed to identify or detect the shear zone and flat and thinly foliated class 5 and class 4 rock mass lying here, fractured and blocky rock mass of class 3 and class 4 classification, crushed and sheared lithogranite and intrusive pegmatite, which were comprising this zone. So it missed detection of mega shear zone and class 4, class 5 rock mass, which were actually present. Crushed and sheared lithogranite and intrusive pegmatite was also missed. Actually, as it is said here, that at least 4 holes were required for a length of around 314 meter and 58 meter depth of the cavern, one like this and 2 inclined, and the other vertical borehole in the other end. These 4 boreholes are needed to represent fully the length and breadth and height above the crown for such a long and deep cavern. Cross-hole tomography is also a good option to resort to find out the geological conditions in such conditions. Inferences from limited geological investigation can miss crucial features and misguide, as we discussed just in the previous slide. In 2010 year, very limited geological investigations were done before the construction of the structure was to be taken. Downstream Surge Gallery site was investigated by the consultants, PHEP-II, based on only one borehole, DSC-1. The other borehole, DSC-3, done by consultants, PHEP-II, was driven at a different and faraway location to that suggested by their geological consultant, GSI. Geology consultant reported, with the only drill core data of DSC-1, it is very difficult to interconnect various bands and enclaves of biotite gneiss. However, the rock to be encountered in powerhouse, transformer hall, and downstream surge gallery is inferred to be fair to good rock as per Q system. So this was the observation that geology consultant could make on the only borehole information, DSC-1, that in all three caverns of powerhouse, transformer hall, and downstream surge gallery, fair to good rock would be encountered. That means that this would result the whole design concept and layout being based on wrong and misinformed geology. Let us see. Lacking geological investigation becomes the genesis of structural instability. If geological investigations are not done properly, then they can become genesis of structural instability. This is what we'll see in the coming slides. There was a shear zone encountered in the main access tunnel to the powerhouse and construction added to the downstream surge gallery. This is construction added to the surge gallery, and this is main access tunnel to the powerhouse. A shear zone was encountered during the excavation of these two tunnels. It was met in 2012. Shear zone was met in construction area and main access tunnel. Same shear zone was apprehended to be met in downstream surge gallery. The resident geologist of the project had predicted or estimated that this shear zone, which was met in two construction tunnels and construction tunnel and main access tunnel, would be projecting and would be also met in three caverns. Actually, these two caverns were also initially having the same start point. So this shear zone was to cut all the three caverns. (314-meter long downstream surge gallery site investigated in 2010 through only borehole downstream DSC-1, which missed mega shear zone, and geology was interpreted as good to fair. This was the only one intersecting borehole which intersected the downstream surge gallery. The other borehole that they had done was far away and it didn't intersect the area of downstream surge gallery. So only one borehole, DSC-1, was available. This is that borehole that was done. This is the downstream surge gallery, and this was the only borehole, DSC-1, done. This is a shear zone which cut the three caverns. The geological inferences might have been based on the sole borehole which would have penetrated fair rock. So what would have happened was that the only borehole that was available had intersected the fair rock, and therefore the geological inference drawn in 2010 by the geology consultant was that the rock encountered would be in all the three caverns would be fair to good. Whereas in actual, the above distribution of rock mass classification was got known only during actual excavation of three caverns. When the caverns had started with excavation in their central gullet, only then the actual geological conditions got to be known. This was the only borehole done in 2010 which inferred the rock to be met to be of fair quality. These rock classifications were remained undetected. The shear zone of 45 to 60 degree dip with an north 30 degree orientation was missed. This very poor rock mass following the shear zone was missed. This rock mass which was jointed and fractured was missed. So the very poor to fair and poor classification of rock mass which were existing actually remained unrepresented in the studies in 2010. These are areas of interest to us: jointed and fractured rock and very poor rocks which follow the reaches just after the shear zone. Now that was a time to account for the actual geology exposed during excavation. When in 2012 those shear zones were met in the construction area and in the main access tunnel to the powerhouse, and later on it was confirmed that in the central gullet of the caverns the same shear zone is intersecting the three caverns throughout their depth. That was the time to account for the actual geology exposed during excavation in the designs of layout and design of rock sports. NGI in their report, which was later on, NGI was requested to give their findings. The NGI in their report has evaluated and found that the quality of the rock encountered is very poor to poor, in contrast to what was assessed as fair to good. The same observations were made during the actual excavation of the central gullet, and thereafter the project authorities geologists had been sending the various various geological features encountered and the classifications based on that to the designers, which the Norwegian Geological Institute later on, when asked to give their finding, had also reported that the quality of rock encountered is very poor to poor, in contrast to what was assessed as fair to good. So if we see, then the poor rock mass in the three caverns comprise of powerhouse 54%, transform cavern 56%, and in downstream surge gallery around 54% lies in the range of poor rock mass, and in downstream surge gallery 4.5% and transform 7.4%, and in powerhouse cavern 1% comes under very poor conditions, and poor to fair are this, and there is no good and fair rock. So actual geology is poor to very poor. Lithogranite with micaceous quartzite, biotite gneiss and pegmatite veins bands, low dip foliations with clay coatings. Class 5 loose rock mass, thinly foliated, highly fractured biotite gneiss with lithogranite and crushed pegmatite, Q values ranging from 0.19 to 0.58, where excavation progressed by chipping and scaling and no blast. In the Q values of 0.19 to 0.58, there was no requirement of resorting to blasting. It was the tunneling and the excavation was progressing by just chipping and scaling. Class 4 altered rock mass Q value 1.5 to 2 with thin shear seams and sheared, crushed and fractured. Highly jointed with clay coating along intersecting joints. Excavation progress with 0.18 to 0.36 kg per cubic meter of charge only. Also, slabbing and wedge failures were predominant in such reach of class 4. Downstream Surge Gallery encountered 14 numbers of shear zones of size 2 cm to 3.5 meter, 7 numbers of major joint sets including foliation joint with low dip and direction 10 degree to 15 degree, southwest to northwest, spacing 0.2 to 0.3 meter. Joints adversely oriented for wedge actions have continuity 10 meter to 15 meter, are generally altered and stained and are showing warping, filled with silty oblique clay material, sometimes filled with crushed material, have 10 mm to 20 mm opening. So such is the geological condition which is referred to poor to very poor. The major shear zone which got missed. The shear zone and thinly foliated, highly fractured biotite gneiss and crushed ricogranite oblique pegmatite got exposed on the left wall near SPL at RD 124 meter to RD 140 meter. The same shear zone which was met earlier in the two construction edit and main access tunnels got met in the Downstream Surge Gallery at RD 124 meter to RD 140 meter, and further at the crown near RD 170 meter there were blocky and jointed rock mass exposed. The major shear zone having dip 45 to 60 degree with orientation 9 north 30 degree was encountered in April 2013 at the crown portion between RD 121 to RD 140 meter and is extending above the crown and below on the entire wall, dipping towards face, gable and wall. Second important information that I want to share is the appropriateness of design of layout and size of caverns. These are guided by the cavern should be oriented in consideration of the orientation of the predominant joint sets, dip and strike. The cavern should be oriented in consideration of the orientation of the predominant joint sets, dip and strike. Joint set strike if it is perpendicular to the cavern axis, then if dip is 45 degree to 90 degree and the drive is along with the dip direction, if the drive is in the dip direction, then if the dip is 45 to 90 degree, dip of the joint set that strike perpendicular to cavern axis, having a drive in the direction of dip, and if the dip of the joint is 45 degree to 90 degree, it is favorable. And if the dip is 20 degree to 45 degree, still it is favorable. But if the drive is against the dip, then the dip of 45 degree to 90 degree is fair, but a dip of 20 to 45 degree makes unfavorable conditions for tunneling in that kind of a situation where the dip of the joint is 20 degree to 45 degree and the drive is against the dip. If joint set strike perpendicular to the cavern axis, if the joint set strikes parallel to the cavern axis, the strike parallel to cavern axis and the dip is 45 degree to 90 degree, they are very unfavorable. If strike is parallel to the cavern axis and dip is 45 degree to 90 degree, whatever is the drive direction, if dip is 45 to 90 degree, these are very unfavorable. And if dip is 20 degree to 45 degree, this is fair. Dip 0 to 20 degree, irrespective of strike, is unfavorable. Punatsangchhu-II projects caverns oriented north 05 degree to west. Foliation joint has low dip 10 to 15 degree. So dip 0 to 20, irrespective of strike, is unfavorable. Here the dip is 10 to 15 degree. Direction is southwest to northwest. Spacing is 0.2 meter to 0.3 meter. Also, there is a major shear zone 45 degree to 60 degree. 45 degree to 90 degree, they are unfavorable. Intersected downstream surge cavern in the middle of its length. So all these conditions make it unfavorable. Time to check the appropriateness of the design of layout and size of caverns. So such conditions when get known, that becomes the time to check the appropriateness of design of layout and size of caverns. The advice of geologists based on geological investigation should be treated as sacrosanct. Geologists in their 2010 observations geological report, had recommended that shear and highly fractured zones may be encountered in the surge cavern. It is strongly recommended to minimize the size of surge chamber as far as possible. Based on the only borehole done in the Downstream Surge Gallery, still geologists could infer from the limited data itself also that there could be shear and highly fractured zones may be encountered in the surge cavern. So they strongly recommended to minimize the size of surge chamber as far as possible. This advice should have been taken to be sacrosanct. But what was the designed layout and size versus geologists' advice? Let us see. Between 2010 to 2013, based on geological investigations in 2010, the geology consultant had reportedly advised that shear/highly fractured zones may be encountered in the surge cavern. It is strongly recommended to minimize the size of the surge chamber as far as possible. However, the DSG cavern size is designed as 314 meter length, 18.8 meter width, and 58.7 meter height. Despite that the rock mass being poor to very poor, instead of what was assessed in 2010 as fair to good, the size and layout remained unchanged for the DSG when it became known in 2013 that the DSG is intersected by shear zone in the middle. The big size of DSG under asymmetrical conditions thus made the Downstream Surge Gallery subjected to high degree of structural instability. Sorry. So, at that point of time, before taking up further excavation, the layout design of caverns should be checked by numerical analysis. Presence of major shear zone not known before, therefore could have not been incorporated in the previous analysis if done before this point of time. in 2013. That means if any analysis was done previous to 2013 based on which the layout would have been decided, in that analysis, presence of major shear zone would have not known. So this point of time in 2013 becomes a stage when the layout design of caverns should be checked by numerical analysis, that whether they are stable with the presence of the shear zone and the type of the rock mass which are following the shear zone. There would be crucial concern on the rock pillar sizes because of the actual conditions of presence of shear zone which cuts across the full depth of the downstream surge gallery. So let us see what are the stipulation on thickness of rock pillars as per international literature. If we refer to an article, Design of Large Underground Caverns, a paper by Sheng, Wai and Liu, Taiwan, in 6th Congress ISRM, Montreal, it recommends the pillar width between the two caverns should be equal to or more than the depth of the deeper cavern of the two. The pillar width between the two caverns should be equal to or more than the depth of the deeper caverns of the two. So, for the case of Downstream Surge Gallery and Transformer Hall of Punatsangchhu-II Powerhouse, the pillar width provided is 40 meter as compared to the depth of the larger of the two caverns of that is Downstream Surge Gallery, which is 58.5 meter. So 40 meter depth thickness of the pillar provided against the depth of Downstream Surge Gallery 58.5 meter. If we have to go by this principle, then it should be at least equal to or more than the depth of the deeper cavern of the two. That means it should be either equal to 58.5 meter or more than 58.5 meter, but not 40 meter, which is provided. So, in consideration of this criteria, the pillar width between Transformer Hall and the Downstream Surge Gallery may have required to be equal to the depth of Downstream Surge Gallery, that is 58 meter, whereas the rock pillar between the Downstream Surge Gallery and the Transformer Hall is only 40 meter against the depth of Downstream Surge Gallery of 58.5 meter, and the rock pillar between the Transformer Hall and the powerhouse is also 40 meter against the depth of the machine hall, which is 52.5 meter. So in both cases, the pillar between adjacent caverns is lesser provided than the stipulated criteria. So what observations were made during the excavation of Central Gullet? Excavation of Central Gullet in Downstream Surge Gallery, Transformer Hall and Powerhouse started in March 2013 on the basis of a sketch issued by designers. Designers were Central Water Commission, which did not include rib sports. So initially, the designs that were provided for the three caverns did not include rib sports. Obviously, for the geological conditions inferred as good, fair to good, there would not be any rib sports required, at least for the Central Gullet. On 2nd May 2013, a 3.5 meter thick shear zone met in the Downstream Surge Gallery at RD 123.5 meter, causing 8 meter high cavity. This shear was met earlier on in August 2012 as in construction added to Downstream Surge Gallery at RD 440 meter, and also on 17 January of 2013 in main access tunnel to powerhouse at RD 420 meter. Understanding that the rock sport and the pillar widths were decided to before encountering the shear, consultants were requested to review designs. The project authorities requested to the Central Water Commission the consultants to review the designs of layout and rock sports in light of these findings that a shear zone has been met in construction added to the Downstream Surge Gallery and in the main access tunnel powerhouse, which by the studies of the resident geologist may also intersect the three caverns. On 11th May 13, designer consultants, that is CWC, issued a sketch showing ISMB 350 rib sports to be provided at locations of chimney, oblique cavity, and similar conditions in the central gullets of all three caverns. Understandably, to provide temporary support like shuttering for backfill and to safeguard from falling loose rock mass. When the shear zone had been actually met in the Downstream Surge Gallery and a cavity of 8 meters had been formed on 2nd May 2013, thereafter on 11th May, the designer's consultant issued the sketch which showed ISMB 350 rib sports to be provided at certain locations of chimney formations and cavity formations in similar conditions in central gullets of all three caverns. Chimney formation, the order of 7 to 9 meter, which had happened at RD 123 meter at the location of where shear zone was met in Downstream Surge Gallery. Such a chimney formation was made and the rib sport was introduced, and these were the rock bolts initially designed to be provided along with the rib sports that the designers asked to provide in all the three caverns in locations where such chimney formations are made during excavation. Fourth point is importance of backing up the designs with construction stage geological investigations. So we saw that the designs provided were based on fair to good geology as was inferred in 2010 investigations that were done prior to construction. So during the construction stage, whatever geology is get exposed, it becomes important to back up the designs with now the construction stage geological investigations. Iterative approach of integration of design and constructions thus is required. Adequate construction stage geological investigation of the site were essential in April 2012, when shear zone was met in the construction area of Downstream Surge Gallery and then in main access tunnel. As already mentioned, that in April 2012 and in January 2013, a shear zone was met in the construction edit and the main access tunnel to powerhouse. At that time itself, at construction stage, more geological investigations were required to be done for the three caverns of powerhouse, transformer hall, and Downstream Surge Gallery. Adequate geological investigations were still required when a major shear zone was met in the central gullet, and uncertainty of geological features in the crown were apprehended by the resident geologist. Now, firstly, in 2012 and in January 2013, the necessity of construction stage geological investigations should have been noticed by the consultants and the designers, and if missed at that time, then at least when the shear zone was actually met, the same shear zone which was met earlier in the two tunnels was then when met in 2013 April in the central gullet of Downstream Surge Gallery. At least at that stage, further investigations of geological conditions was required for review of designs, and that too when resident geologist of the project had apprehended that geology remains very uncertain above the crown. Actually, the resident geologist had mentioned it in his reports that the geological conditions were so frequently changing that it was very difficult to predict geological conditions beyond a depth of 1 meter above the crown. Iterative approach required review of design of orientation and layout of underground structures at this stage of central gullet excavation. Now when it became evident that the major shear zone dipping at 45 to 60 degree would cut across the three caverns throughout their depth and almost in the middle of these caverns, then it became very important to review the design of orientation and layout of these underground structures when the excavation was still in the central gullet. The central gullet is only of the size of 7 meter depth, whereas the full excavations were to be done through the depths of around 58 meter, 52 meter to 58 meter. Then at that time, the review of layout of the three caverns was necessary. Inference on geology and stability need be drawn from each stage of excavation. So it becomes an important learning that inferences on geology and stability need be done from each stage of excavation. Situation was at offing of crucial fallout. Cavity formation in transformer hall at RD 140 meter of 7 meter height on 15th July 13 in Central Gullet. Regularly supplied 3D geological mapping and geological notes informing persistent existence of crushed pegmatite and water seepage was provided by the resident geologist. The rib sport was added to the rock sport system in all the three caverns. So based on these geological conditions reported, the designers Central Water Commission had included rib sport for all the three caverns in the Central Gullet itself. Informed to designers that installation of rock bolts were being possible and done after rib erection and backfilling. It was also mentioned because of the very poor geology, it was not being possible to provide installation of rock bolts immediately after the excavation, but only it was possible only after the rib erection and backfilling. Informed to designers that cavity formation in transformer hall where shear zone touched transformer hall at gable end and at RD 191 to 214 meter required face plugging. So the conditions in the transformer hall cavern were so bad that it required face plugging at RD 191 meter to 214 meter near the gable end. Information by the resident geologist that it was not possible to predict geology beyond a depth of about 1 meter beyond periphery of the excavation due to excessively changing characteristics of rock mass was also informed. On 11 September 13, before starting side slashing in the Downstream Surge Gallery, when Central Gullet reached RD 208 meter in Downstream Surge Gallery, it was suggested to the designers by project authorities to consider providing a wall beam and cable anchors in Downstream Surge Gallery to cater to poor to very poor rock conditions. Now, at this stage, before proceeding with side slashing to increase the width of the excavated Central Gullet in the Downstream Surge Gallery, project authorities requested to the designers CWC that wall beam and cable anchors need to be provided in the poor to very poor rock conditions to be met in the Downstream Surge Gallery at least. The other two caverns, powerhouse and transformer hall, based on the resident geologist advice, were shifted by a length of 18 to 36 meter so as to avoid cutting by the shear zone in the middle of their lengths, and that only their gable ends could remain, if at all, intersected by the shear zone. But somehow the transformer hall, somehow the Downstream Surge Gallery was left to be still intersected by precariously by the major shear zone, and for that reason, at that point of time, before starting the side slashing, the designers were requested by the project authorities to provide wall beam and cable anchors in the downstream surge gallery's such reach where it is intersected by the shear zone. So this was the time when it needed to review initial stage of at the excavation. The layout and design of the three caverns was needed to be reviewed based on the exposed and further projected geology. This was the shear zone which was met in 2012 and January 2013 in the two tunnels of main access tunnel to powerhouse and construction area to downstream surge gallery, which was projected to be intersecting the three caverns. Actually, this drawing is showing the layout of the three caverns as is constructed finally. However, powerhouse was 36 meter behind this point and starting only in the same alignment of that of downstream surge gallery. This is downstream surge gallery. It starts from here. Transform hole cavern is this, and it was also starting from here, and powerhouse was also starting from here. So by that, these if were initially to be having their gable end here, then the shear zone was also to cut across transformer hall and powerhouse cavern. But based on the geologist's advice, the powerhouse and the transformer hall was shifted towards south end by 18 meter and 36 meter each, so as that this shear zone finally did cut the transformer hall at its gable end only, and its affected zone merely touched the powerhouse cavern at its gable end. But somehow this downstream surge gallery remained unchanged. Designers did not change or reviewed its layout or design, and it remained cut by the major shear zone throughout for its depth. So this was the time when the layout of the downstream surge gallery should have also been reviewed, when the layout of these two caverns was done. Review of the layout of the powerhouse and transformer hall caverns. Another shear zone met in downstream surge gallery at RD 130 meter. Geological mapping was provided regularly to the designers. On 14th June 13, project authority suggested to designers shifting the three caverns on the basis of 3D wedge analysis carried out by chief geologist of the project to avoid cutting by shear zone. Only location of powerhouse and transformer hall caverns were shifted by 36 meter and 18 meter, which avoided cutting of powerhouse by shear zone, whereas the transformer hall it helped in getting only marginally touched by shear zone at northern gable end. However, the downstream surge gallery, which is most critically poised and is of maximum size, its layout and location was left unchanged. Encountered field conditions during excavation, if are in contrast to the envisaged, it requires review of design and analysis of structural stability. Now, having the downstream surge gallery left unchanged for its layout and orientation, at least the structural stability needed to be ensured through a reviewed design, as was mentioned in the Hook and Brown flow chart, which I discussed in the beginning, that if the orientation and layout of a structure is not possible to safeguard it by from the poised instability because of inclined geological structural features, then the structural stability has to be improved by providing properly designed rock support measures. So in this case, because of the encountered field conditions during excavation, which was in contrast as they were envisaged initially when the rock classification was inferred as good to fair. Now, at this point of time, it required a review in 2013 May. Designers were informed since 2013 May through February 2014 before start of site slashing that a rockbolt support system in the center gallets is becoming possible to be provided only after installation of the ribs. Presence of pegmatite veins despite of use of charge factor of only 0.19 to 0.8 kg per meter cube were leading to frequent rockfall and wedges were being detached, affecting crown profile and arching action of the roof of caverns. The clear indication of the extent of weakness of rock mass actually encountered warrant analyzing caverns again with the actual parameters to evaluate whether on benching to 58.5 meter depth the cavern's structural integrity shall remain intact in the poor to very poor rock mass met with adverse mega shear zone. So the clear indication of the extent of weakness of rock mass actually encountered warranted analyzing caverns again with actual parameters to evaluate whether on benching. Now in the 2013 only 7 meter of depth of central gullet was excavated and it was to be benched down to 58.5 meter. So it was necessary to evaluate the structural integrity of the cavern when it would be excavated to its full height, whether it will remain intact or not when the rock conditions is actually poor to very poor rock mass and is on that also is cut down by is intersected by adversely oriented deep and sharply dipping mega shear zone. So it became important a timely review of structural stability before further proceeding with excavation becomes important in such condition. Preliminary analysis raised apprehensions on stability. A numerical analysis was done by engineers of civil contractor engaged for construction of powerhouse. Designers were presented by a numerical analysis that was done not by the designer but by the engineers of civil contractor engaged for construction of powerhouse. The analysis showed yielding to great and severe extent in rock pillars, oblique walls, upon progress in excavation and potential collapse, oblique failure. The designer consultants were apprised of the analysis carried out and results. Eventually, the huge rock mass failure in Downstream Surge Gallery happened on 3rd March 2016 when excavation in Downstream Surge Gallery had progressed to about 45 meter depth out of its total depth of 58.5 meter. So, the civil engineers of contractor had come out with a numerical analysis which was presented to the designers consultants, that is CWC, Central Water Commission, and that analysis at that time had showed that if the excavation is progressed to its 2/3 height or even beyond that to its full height, there will be huge yielding happening to great and severe extent in rock pillars and walls upon progress in excavation, and a potential collapse oblique failure would be imminent. That was established in the initial analysis done by the contractors, engineers, and that was presented to the design consultants, Central Water Commission. Now, international literature cautions rejections of such site for large caverns, as was seen by us in that flow chart, which mentioned intersected by massive shear zone. Talking of the present conditions, intersected by massive shear zone which formed the hanging wall. Moreover, the hanging wall comprised highly jointed blocks of rocks with joints filled with crushed rock and clay and intrusive pegmatite. Such conditions, if are compared with what is mentioned in underground excavations in rock by Hook and Brown, Hook and Brown's literature mentions at its page 10, in rock masses with strongly developed inclined structural features, excavation stability may be dominated by the gravity falls and sliding along inclined discontinuities. So, excavation stability may be dominated by gravity falls and sliding along inclined discontinuities is mentioned. At page 299 in the same article, it says, it says, rock mass with adjusted total classification ratings of less than 50, when is heavily jointed, it will tend to behave like an assemblage of tightly interlocking angular particles with no significant strength under unconfined conditions. So when the conditions would become unconfined, it would not have any significant strength in the presence of inclined structural features. So large caverns should only be excavated in rock with adjusted total classification ratings of 50 or better. The RQD rating for Downstream Surge Gallery stands valued of the order of 40 only. So it does not encourage excavation of deep caverns, and the same was cautioned against by Geological Survey of India, the geology consultants of the main consultants, in their investigation report in 2010 itself. The Geological Survey of India had also recommended that the Downstream Surge Gallery should be having a restricted size and large cavern should not be made for Downstream Surge Gallery. And the same thing is reiterated here, that because of the RQD rating is 40 for Downstream Surge Gallery, and this literature of Hook and Brown says that if it was not better or at least equal to 50, the large cavern should not be excavated in such rock. So, four important concerns which required responsive attention with progress of excavation in such situations are: review of layout of Downstream Surge Gallery, review of size of Downstream Gallery to network of multiple smaller tunnels and chambers. So how the size of the Downstream Surge Gallery should have been restricted was by resorting to changing its layout to multiple smaller tunnels and chambers. Then review of width of intervening rock pillars which is intersected by shear zone and comprised of fractured rock mass. What are the important concerns which should have been addressed was review of layout of Downstream Surge Gallery, review of size of Downstream Surge Gallery by resorting to making it of multiple smaller tunnels and chambers. Then its pillar widths, intervening rock pillars should have been also analyzed and seen if they are when they are made of comprised of fractured rock mass, whether the existing size were proper or not. This should have been established. Strengthening of intervening rock pillars by providing cable anchors and wall beams. So as was requested to the designers, it should have been seen that whether the rock pillars need be strengthened by providing cable anchors and wall beams. These are the four important concerns which should have been tackled at that point of time in 2013 for such geological conditions in Downstream Surge Gallery. So powerhouse complex with shifted layout is like this, that the major shear zone dipping towards this direction at 45 to 60 degree cuts this Downstream Surge Gallery almost at its middle length for its full depth. It cuts transformer hall near its gable end, very near its gable end, and it merely touches the powerhouse gable end. after these two were shifted by 36 meter and 18 meter towards south. So in three-dimensional view, the steep shear zone did cut across in the mid length of the downstream surge gallery. This is downstream surge gallery. It cuts it in the middle length. While it was avoided in the transformer hole, it was almost avoided to cut it in the middle length, and it affects only in the little length of the gable end, and in the powerhouse it merely touches it. Gable end provided confining support in powerhouse and transformer. So by shifting these two caverns to south side and avoiding the shear zone to cut it considerably in its almost middle, the two caverns of powerhouse and transformer hall were saved by providing them a confining support in their gable end reach. Because there was gable end, so there was confinement conditions provided in the near vicinity of the shear zone. Whereas that confinement, because the gable end of the downstream surge gallery was very far off, so such a confinement of the rock masses was not possible, and the degree of freedom for movement of the rock masses was very much there because of the presence of shear zone in the downstream surge gallery. If shifting downstream surge gallery was not feasible, its size needed to be restricted by bifurcating downstream surge gallery to isolate the shear zone affected part and resorting to adding tunnels to make up for the volume. So what was possible if its shifting was not possible was that at least bifurcate the downstream surge gallery into two portions, leaving the middle portion which was affected by shear zone and compensating the part which was lost because of the shear zone by adding additional tunnels and chambers connected to the two parts of the downstream surge gallery. That could have been done to restrict its size as was advised by the geology consultant in 2010. So, sixth important point is on knowing presence of major shear, the layout design of caverns need be checked and reviewed by the numerical analysis incorporating the actual geology. Now, at this stage, a numerical analysis should have been done by incorporating the shear zone and the actual geological conditions which followed the shear zone. Now, the 40-meter thick pillars which were designed initially in 2010 would have been rendered deficient because of the presence of the shear zone cutting this pillar and the wall of the downstream surge gallery. So this was stipulation on thickness of rock pillars as per international literature. Design of large underground caverns by Sheng, we have seen that it mentions that the pillar width should be equal to or more than the depth of the deeper cavern of the two. So by that criteria, it need to be provided to be 58 meter instead of 40 meter. And this is the analysis in 2014 that showed yielding of rock mass of the rock pillar in downstream surge gallery, which was done by the contractor engineers. And this large scale yielding, when the cavern was downstream surge cavern was seen to be excavated for its 2/3 and full height, large scale yielding was seen in the analysis, and it was mentioned to the designers. Requirement of strengthening of pillars. So at that time it required a requirement was established that strengthening of pillars was needed. Need of providing cable anchors and wall beams was requested by the project authorities. If we refer to the underground excavations in rock by Hook and Brown, it says four principal sources of instability are identified in the chart in page 10. Instability due to adverse structural geology tends to occur in hard rocks which are faulted and jointed and where several sets of discontinuities are steeply inclined. Stability can sometimes be improved by relocation or reorientation of the excavations, but fairly extensive support is also usually required. Rock bolts, dowels, and cables are particularly effective when used to support this type of rock mass, provided that the structural features are taken into account in designing the support system. So, in design, now the merely based on Q system would not work. It has to take into consideration specifically the structural features the which comprise the geology. All the joints, their dip, the shear zone, all these parameters need to be taken into account to do a numerical analysis and find out whether the designs are adequate or not. The designs provided for structurally good geology conceived initially in 2010 were addition of rock bolts and anchors and steel ribs, which don't add up and may not be sufficient for actual encountered structural geology. The designs provided at locations of shear zone class 5, class 4 have been rock bolts, one set of which were held within the shear rock mass. These may be too less a treatment to withstand shearing forces put by structural features. Now, talking of the pillars which are intersected by the shear zone, the designers had given additional crisscross rock bolts to stitch the shear zone. But what was happening was that out of the crisscross shear zones, the one set of the rock bolts were having their end provided in the sheared zone only, which was making it ineffective. So effectively only one set of the rock bolts were getting effective, and they may be too less to provide a strength to the pillar to the kind of stresses they would be subjected to, because they will be subjected to shear, not a longitudinal stress, but a shear stress. Shear zone and very poor rock in downstream surge gallery from RD 124 to 185 meter, having not strengthened by wall beam and cable anchors as was requested by the project authorities. The steel ribs in downstream surge gallery had sunk in 2014 in both walls from RD 130 meter to RD 170 meter by 20 mm at crown, resulting in 55 mm gap created between the ribs and the cladding. So initially itself it was showing that the steel ribs had sunk in 2014 in both walls of the downstream surge gallery at RD 130 to 170 meter. Behavior of the unconfined fractured class 5 and class 4 rock mass, which rested upon the shear plane. So the fractured class 5 and class 4 rock mass got unconfined because of the side conditions, and such unconfined rock mass was resting on the shear plane. This hanging wall comprises of the jointed and fractured rock. Because of the presence of this shear zone, this became a footwall and this became hanging wall. And this hanging wall comprised of the jointed and fractured rock which was resting on the shear zone. As excavation proceeded, this hanging wall got unconfined, and this was comprising of jointed and fractured rock of very poor to poor classification, which became unconfined. Interaction of rock pillars by shear zone and crushed and fractured rock mass. Between 2014 to March 2016, the shear zone made downstream surge crown and both up, downstream surge galleries upstream wall and downstream wall through and through over their full depth from RD 130 meter to RD 180 meter into a pre-cracked crown and pre-cracked pillar, which were free to slide on the already yielded shear plane, as there were not to be transmission of stresses possible through the yielded shear zone. What it says is, this is upstream wall of the downstream surge gallery and this is downstream wall of the surge gallery. This is being, both are being cut through and through by the shear zone between RD 130 to RD 180 meter. Because of this walls and the crown, this much is a representation of the crown and this much is a representation of the wall beneath crown and the wall. So because of the presence of this shear zone, this crown and the wall, they are as if they are pre-cracked and they are free to slide on the shear plane. They are free to slide on the shear plane. Now, seventh important in the iterative method was instrumentation. Now, what does instrumentation during excavation had revealed in Downstream Surge Gallery of Punatsangchhu-II project, and the importance of inferences drawn from instrumentation during excavation. This is the kind of instruments provided in the Downstream Surge Gallery at RD 40, 80 and 135 meter. There are multiple extensometers, 3-point MPBX, surface targets, anchor load cells of rock bolts, pore pressure cells at such locations and elevations are provided. Now, arrangement of instrumentation in Downstream Surge Gallery with respect to the shear zone. This shear zone is cutting throughout the depth of the Downstream Surge Gallery and dipping at 45 to 60 degree from south to north, like this. Like this it cuts. And the observations in the instrumentation was that when benching had reached elevations 608, then distress at elevation 620 meter in Downstream Surge Gallery upstream wall at RD 135 meter mentioned that there was no distress is seen in the load cells or in the MPBX to the depth of 25 meter, whereas the surface targets showed movement X16, Y14, -14, Z19, X13, Y -26, Z5 kind of, X22, Y -28, X22, Y -34, like that, which showed there was a bodily shifting happening and stresses or de-stresses were not there within 25 meter of the depth of the rock from the excavated surface of the cavern. Similarly, at elevation 620 in the downstream wall of the surge gallery also, there were hardly any distresses seen in the body of the up to 25 meter depth of the rock from the excavated profile, whereas The surface movement was seen in the targets. That shows there is a bodily shifting of the rock mass. Similarly, at elevation 624, downstream Surge Gallery's downstream wall at RD 180 meter also showed the same trend. There were no distresses within the body till October 15. Till October 15, there were only surface targets that were showing movement, and it indicated a bodily shifting with no distress within the rock mass to certain depth. And on October 15, only some stresses started getting seen, distresses started getting seen in the rock mass in the near vicinity of the surface of the excavation profile. So it indicated the arch action was intact in the crown on the downstream surface. Excavation of benching in the shear zone reach from elevation 615.8 meter to elevation 608 meter near RD 135 meter had been through June to November 2014. Sudden sinking and drifting bodily of the arch at RD following locations intercepted by shear zone at haunch portions in the wall occurred in November 2014. As mentioned earlier, that it was observed that the ribs had sunk in both the walls of Downstream Surge Gallery in November 2014. Trend of increase in load, though not very significant in the load cells installed in the arch, happened in May 2015 after benching in walls had progressed up to 596 meter. The distress in the rock above crown had not developed any significant distress till sudden fall of the crown 3rd March 2016. Arch was intact as rock mass of about 25 meter thickness, as MPBX is only of 25 meter length, did not show any significant stress. So the important observation is that within the thickness of around 25 meter, which is equal to the length of the MPBX, so it can be observed that at least to a depth of 25 meter into the rock from the excavated profile, there were no distresses seen in the crown. Therefore, it can be said that at least an arch of around 25 meter thick was intact till 3rd March when distresses had seen developed in the MPBX also. The load cell installed in the crown had developed excessive load by 2nd March 2016. So only on 2nd March 2016 there was excessive load shown in the load cell in the crown. So this was the shear zone, and the north side portion of the Downstream Surge Gallery, which was resting on the shear plane, was showing bodily drifting towards X, that is towards this side, towards the downstream wall side, and sinking as well as drifting towards north direction, as if this was slipping on the shear plane. And distress in 609 meter elevation at RD 135, when benching had proceeded further to 605, then the surface targets were seeing displacements of the order of x8, y-11, z7, and there is some distress also seen. So with the progress of benching, now we see that there are displacements within the 25 meter reach of the walls, and at the surface they are happening. Similarly, at RD 180, at 609 meter elevation instrument, when the benching had reached 599 meter, 590, 590, 587, when benching is progressing, the stresses are and the movements are increasing, and the distress in the walls are also suddenly showing. Same thing. So as explained earlier, it was as if this was sliding. Rock mass was sliding in the hanging wall on the shear plane. The walls, the reach in the walls in the shear zone and associated weak rock mass had been supported with a concrete cladding and two sets of 15 meter long, 36 meter dia rock bolts, followed by consolidation grouting. So designers had asked to provide these stitching rock bolts over a concrete cladding in the portion affected by the shear zone. But what was happening was that one set of shear rock bolts was having its end landing in the shear zone and fractured rock only, while the other set was having its anchor end ending in the sound rock. So that was effective, but this set, which with their anchor to be provided within the fractured and sheared zone, were not effective. Reviewing of design parameters so as to be validated by field observation. It is a must to do validation and review of design based on instrumentation at various stages of excavation. Instrumentation observations cautioning a destabilizing trend, the review of stability analysis of the underground structure at each critical stage of excavation, incorporating the latest geological condition becomes imperative. So having this set of observations from the instrumentation, it called for validating the design parameters that were used, if at all, in the analysis. Then the review of the design parameters was necessitated to make the design reveal the same amount of distresses and stresses as is seen and observed in the instruments. So eventually on 3rd March 2016, the rockfall had happened. 6 workers got killed and 91 meter high, 45 meter wide and 70 meter long cavity was formed. At that stage now, it was taken upon to do scrutiny of backfill and grouting. A number of test boreholes were done and videographed through after the massive rockfall had happened in order to confirm that whether the over-excavated reaches in the powerhouse, transformer hall and downstream surge gallery caverns roof had been properly backfilled and grouted previously or not. All the boreholes confirmed that there were no cavities or unfilled zones found existing above the crown, and also there were no open cracks found, which confirmed that the excavated reaches had been properly backfilled with concrete and also had been adequately grouted previously. So, vulnerability of the downstream surge cavern between RD 145 meter to 195 meter, 3D analysis done later in 2018 by NIRM, National Institute of Rock Mechanics, corroborates that due to existing geological conditions, there had been excessive yielding in the rock mass in the truncated upper half of downstream surge gallery, which was lying along the traverse of the shear zone in the rock pillars. The NIRM analysis done in 2018 ratifies that hanging wall side stood yielded. No precision of wall beam and cable anchors to strengthen the wall of downstream surge gallery, which were designed of only 40 meter thickness, despite that these pillars were intersected critically by mega shear zone. A 3D numerical analysis incorporating actual geology should have been done to establish structural stability of Downstream Surge Gallery and powerhouse between. It should have been done between 2014 to March 2016, but it was not done. The 3D numerical analysis done independently in 2018 only shows that rock mass in Downstream Surge Gallery rock pillar oblique walls yielded up to 15 meter from RD 145 meter to RD 195 meter. So the reaches lying on the shear plane to a depth of 15 meter between the RD 145 to RD 19 meter were standing yielded. Three-D numerical incorporates that the pillars of Downstream Surge Gallery were inherently weak due to presence of shear zone and existing geology at the stage of even thus far excavated depth of Downstream Surge Gallery. So far, only 30 meter to 45 meter depth of Downstream Surge Gallery had been excavated, and they were yet to go to 58.5 meter. But with this excavation itself, there were rock pillars seen to be inherently weak with yielded rock up to 15 meter inside the pillar. At RD 146, RD 156 and beyond, it was seen. The rock is yielded. And in that analysis done by Niram, it is seen that the confining stresses are becoming less than zero above crown in hanging wall side of the shear zone. In the hanging wall side of the shear zone, this area above the crown in the Downstream Surge Gallery, the confining stresses have become less than zero. Confining stresses are less than zero. Confining stresses are less than zero above crown in the hanging wall side of the shear. So there is no confining force to keep poorly jointed rock mass stay together in the hanging wall. Factors adversely affecting the downstream surge cavern: geometry of hanging wall, fracture sets made by subvertical and other joints, variability in strength of rock mass, and loss of confinement. This also becomes a major issue, loss of confinement. International Journal of Rock Mechanics and Mining Sciences mentions of progressive leveling, stress instability and design of underground excavations by C.D. Martina, P.K. Kasarov, and R. Christianos mentions in their article a case study where progressive leveling has been seen. Figure 22, plan view of open stopes and stopping sequence. Stop 3300 was stable until mining of 3400 stop commenced. This is stop 3300 and this is stop 3400. So it says until the stop 3400 was started excavating, the stop with the number 3300 was intact. Now about the geometry of the stop. This is the hanging wall, this is a foot wall, this is the stop 3300, and there is a drift here, there is a drift here. The massive sulfide ore zone at depth of was 300 meter, a long strike and 45 meter in width from footwall to hanging wall, and dipped between 65 to 85 degree. This dip is around 65 to 85 degree. This is around 45 meter in width, and this is around 300 meter long. The transverse stops averaged 35 meter in width, 45 meter in length, and over 180 meter in height. Experience at mine indicated stops of these dimensions were stable. However, number 3300 stop, which had similar good quality rock mass conditions, experienced significant hanging wall problems. The hanging wall rock mass consisted of blocky norites with one subvertical joint set at approximately 1 meter spacing and a second set of horizontal continuous joints also at approximately 1 meter spacing. These fracture sets formed potential wedges in the hanging wall and back of stops. However, simple wedges do not usually lead to progressive leveling, particularly when the geological strength index ranges from 60 to 85, compressive strength 25 to 100 MPa, tensile strength -4 to -2.65 MPa, and EM 27 to 80 GPa. Leveling occurs when confining stress is less than 0. Vertical section through 3300 stope looking towards the mine west showing contours for stress sigma 3 ranging -1 to 0 here at location of leveling. If we see, then the cavity that had formed has this profile, and these stress contours are showing sigma 3 less than 0 and -1, and they show this region has lost the confinement. The stresses have become less than 0. Mining of stope 2900 to 3300 was carried out without incident, with stope 3300 remaining open and stable for approximately 1 year. The mining of stope 3400 was coincident with the leveling of the 3300 hanging wall. Figure shows that because of the stope geometry, a zone of relaxation extends several tens of meters into the hanging wall of the 3300 stope after 3400 stope was excavated. It is evident from figure that failure of leveling occurs when the confining stress is less than 0. So the important thing learned from here is that the failure or leveling occurs when confining stress is less than 0. So in our case also, the NIRAM analysis had seen that the confining stress above the crown had to a large extent had become less than 0. Two forms of instability are readily observed around underground openings: structurally controlled gravity-driven process leading to wedge-type falls of ground, seen in crown in DSG, stress-driven failure or yielding, seen in walls. While the maximum stress near an excavation is sensitive to variation in stress magnitude and stress ratio, it is a variability in the rock strength rather than stress. Variability in the rock strength rather than stress that is responsible for frequently observed variability in depth of failure and failure mode in general. So it is a variability in rock strength which is causing variability in depth of failure. The hanging wall side in downstream surge gallery reduced from presence of major shear zone the hanging wall side in downstream surge gallery resulted from presence of major shear zone comprised multiple shear seams and blocky rock mass fractured by adversely oriented joints filled with clay and fractured rock mass, thus caused variability in rock mass strength. Because of the presence of adversely oriented joint filled with clay and fractured rock mass, they caused it variability of rock strength. Now this variability in rock strength is responsible for frequently observed variability in depth of failure. Now the leveling would occur because the stresses have become less than 0, and because of the variability in rock mass strength, the depth of failure is influenced to large extent. The loss of ductile behavior of lack of confinement pressure and increased yielding explains sudden failure in DSG. It was observed that on March 2016, the crown which had been standing intact for 3 years, like the stope 3300 which stood intact for 1 year, in the Downstream Surge Gallery of Punatsangchhu project also stood intact for 3 years, but it suddenly fell, making a huge cavity on 2nd March 2016, and it is explained because of loss of ductile behavior of for lack of confinement pressure and increased yielding. The experiments on the effect of strain rate by author Sargenti and Boozer show that increasing the strain rate makes rock appear more brittle. More evidence is presented by Robinson and Schwartz. It is observed that the higher the confining pressure, the greater the ductility observed. So, if the confining pressures are higher, it will remain ductile. But if the confining pressures are made less than zero, it becomes brittle. Instability mechanism of underground caverns. Gravity-induced structurally controlled block movement cause structural instability. Accompanied by loss of confining stresses, it can produce raveling. So in such a condition, when gravity-induced and structurally controlled block movement is possible, it causes structural instability. Gravity-induced and structurally controlled. Gravity-induced and structurally controlled block movement. Further, if there is confining pressure becoming less than zero, it causes raveling. So, three conditions: gravity-induced and structurally controlled block movement that causes structural instability. Added to this, if the confining pressures are less than zero, then it produces raveling. Second instability mechanism is stress-induced spalling due to adversely high rock stresses. When the major principal stresses are so high that it causes spalling. But in case of Punatsangchhu-II, in the crown, this mechanism is effective where there are gravity-induced structurally controlled block movement. And added to that, the confining pressure are less than zero, which has produced raveling. So, failure mechanism in Downstream Surge Gallery. Failure mechanism: increase of distress and yielding in the walls resting on shear zone upon progress in benching in Downstream Surge Gallery led to withdrawal of support to crown. So, if this is the rib resting on the wall which is having shear zone cutting it, as and when the hanging wall side comprising highly jointed and fractured rock mass with weak intrusive material was rendered unconfined, lack of confinement causes brittleness. After massive yielding, the walls might have settled suddenly and slid on the shear plane, and the rib lost their bearing. Eventually, the ribs and the crown fell down. As the benching is progressing, the lack of confinement is causing brittleness, and with massive yielding, the walls might have settled suddenly. The walls might have settled suddenly, and load from the arches. The supports under the bearing had failed. Unconfined hanging wall slid on the shear plane, and the ribs and the crown fell down. The confining stresses are less than zero, as we saw earlier. This is producing brittleness and raveling. This lack of confinement to blocks in Downstream Surge Gallery in hanging side, while in powerhouse and transformer hall confining pressure was present. Here the gable end is very near, so the confining pressure is provided by the gable end in both the cases. So the brittleness was not to the extent as is happening in the Downstream Surge Gallery, and raveling was not possible because of the confinement pressure are not becoming less than zero in both these cases. Gravity-induced and structurally controlled block movement cause structural instability. So first thing is gravity-induced and structurally controlled block movement. Because of the geometry of the joints and the clay-filled and fractured mass-filled joints, there is gravity-induced and structurally controlled block movement which caused structural instability in the crown. Lack of confinement in blocks of rock mass having discontinuities with open and clay-filled joints in downstream surge gallery in its hanging wall side resulted from absence of stress around shear zone. Increase of distress and yielding in walls resting on shear and fractured mass upon progress in benching in downstream surge gallery led to withdrawal of support to crown arch. Crown imploded suddenly along structural discontinuities due to associated brittleness resulting from lack of confining pressure on blocks of rock mass and withdrawal of bearing support from yielding walls. Raveling occurred through a zone where confining stress was less than zero. The shape of the cavity above the crown was thus controlled by the discontinuities under lack of confining stresses. Hook and Brown mentions heavily jointed rock mass behaves like an assemblage of interlocked angular particulars with no significant strength under unconfined conditions. The heavily jointed block rock mass suffered brittle failure and resulted in raveling of rock blocks one after another. Loose fall of large rock blocks. The fallen rock mass comprise variable size fragmented rock pieces, sandy clay and dry clay fractions with block rock blocks, maximum size 9 meter into 1.5 to 3 meter. This clearly indicates that failure of rock mass is not restricted to only within the shear zone and its adjoining weak rock material. The rock fall involves loose fall of large rock blocks due to the gravitational forces acting on the blocks, all of which were loosely held due to absence of confining pressure and presence of clay and shear content in their joints and due to large presence of intrusive and pegmatite veins and bands. Sudden formation of huge cavities is because of geometry of hanging wall, fracture sets made by subvertical and other joints, variability in strength of rock mass, loss of confinement makes rock blocks loosely held and rock mass brittle, results in suddenly raveling of loosely held rock blocks, making the rock blocks fall under gravity one after the other. So this defines the whole process and mechanism behind the formation of the huge cavity. Geometry of hanging wall, fracture sets made by subvertical and other joints, variability in strength of rock mass, loss of confinement makes rock blocks loosely held and rock mass brittle, result in suddenly raveling of loosely held rock blocks, making the rock blocks fall under gravity one after another. And variability in strength of rock mass is giving rise to the extent of failure. That means the size of the cavity is being controlled by variability in the strength of rock mass. This mechanism is corroborated in the Norwegian Geotechnical Institute's finding also. NGI's finding on the failure mechanism implies failure happened along structural discontinuities. It mentions that failure happened along structural discontinuities resulting from lack of confining pressure on blocks of rock mass. So NGI report also says that failure happened along structural discontinuities resulting from lack of confining pressure on blocks of rock mass. This is fault plane. NGI reported that the shape of the cavity is controlled by the discontinuities at the study site. So this is the shape of the cavity is controlled by the discontinuities at the site. NGI's findings on the mechanism. The shape of the cavity is controlled by the discontinuities at the study site. It is clear that the major mechanism of the rock fall was structurally controlled block fall. Structurally controlled block fall is to be noticed. The orientation of the maximum horizontal stress is parallel with the axis of the downstream surge gallery. which does not help to prevent the rockfall through confining on the rock blocks. So absence of confining pressure is also mentioned in their report of NGI. The orientation of the maximum horizontal stress is parallel with the axis of the DSG, which does not help to prevent the rockfall through confining on the rock blocks at the roof. It further says the rock mass in the footwall with respect to the shear zone first started to move down because of the insufficient support and stress relaxation. Later on, as the key block in the footwall moved, the rock blocks at the hanging wall moved down flowingly, that is raveling. So this also mentions, NJ also mentions that as the key block in the footwall moved, the rock blocks at the hanging wall moved downward flowingly. That was a sudden failure. No twisting seen in the fallen ribs indicative of failure in the shears at the rib joints. So NGI also finds that the ribs, the curvature of the rib were intact. There were no twisting seen in the fallen ribs. That means the ribs would have failed at their rib joints under shear. NJ findings ratify failure hypothesis. Crown remained intact for 3 years until the distress in the walls, which increased with progress in benching, resulted in extensive yielding of the walls. It thus failed bearing support for the crown. The arch section in the crown eventually became unstable and ribs fell apart without even subjected to any excessive load. The crown, bereft of the wall support, suddenly fell down with the raveling of blocks. The Norwegian Geotechnical Institute has mentioned in its findings that the ribs do not show any sign of deformation and the rock pillars are more loaded. Implies that the ribs have not failed as an individual structural element but failed in the assemblage due to withdrawal of support. It ratifies the theory that ribs have failed not because of excessive load but due to sudden impact resulted from failure of the walls in providing bearing support at the SPL due to excessive yielding and settlement in the walls. The view of the cavity from the southern side in the Downstream Surge Gallery. So this is the fallen rock mass and this is the cavity which extends. This is the ripped portion of the ribs, and it extends 70 meter along the length, and the cavity extends 91 meter above the crown, and it extends 45 meter in width. Assessment of the size of the cavity was done by tomography, and this size was revealed. A camera assessment of cavity was also done by LiDAR technology using CMS 500 camera. And finally, this cavity was detected. Thank you. I hope I am able to explain what in my thinking the mechanism was behind the failure of the rock mass in the Downstream Surge Gallery, which extended to make a cavity of 91 meter high, as is explained in my presentation, and is also corroborated by Norwegian Geotechnical Institute and also by the National Institute of Rock Mechanics. So I hope this will give an insight into the rock mass behavior in such large caverns and will be a guiding source of guidance for designers as well as for construction engineers. Thank you so much.